как значит, вы запустили, что еще раз? Трансляцию. Так, хорошо. Значит, работает ли звук? 1, 2, 3. Давайте посмотрим. Если звук не работает, значит, это значит, что нужно что-то менять. Возможно, батарейки. Может, вообще все. Так, звук работает. Хорошо, тогда давайте начнем. Go. Okay, so last time we started talking about the Dirac operator. And well, let's recall what we need to have in order to define the operator. So we need to have a Riemannian manifold. We need a vector bundle, which is at this point it's well, it's just a vector bundle. Well, let's say we have a metric on this vector bundle. And we assume that all metrics are parallel, both on the cotangent bundle and on S, which simply means that the connections are metric, compatible with the metric. And we also need a Clifford action. And we need two assumptions. assumption 1, each unit, each covector of unit length acts orthogonally on the fiber of S, and the Clifford action we also assume to be parallel. Then and then there exists the Dirac operator, which takes sections of S to sections of S, and the no, it's probably the other way around. Anyway, I never really remembered which index goes up and which goes down. Anyway, these are covectors. A family of orthogonal cotangent vectors or covectors, which are defined in a neighborhood of some point. Now, this is the family of dual to this one. What does it mean? Well, here is what it means. And well, basically from this formula, it's and from another formula we had for the symbol of nabla. It's straightforward to check that the symbol is Clifford multiplication by psi. The symbol attacks psi is Clifford multiplication by psi. What does this mean? Well, psi lives inside the Clifford algebra, and so in particular we can take a psi, view it as an element of the Clifford algebra, and apply it to an element of S. Okay. Now, are there any questions? No. It would be if there weren't an EI here, and when I write EI, this means I take the cotangent component of the nabla without the EI, and then apply it to EI. Basically, what do we have? We have the sections of X, and they go to the sections of S cross so the sections of S go to the sections of S tensor, the cotangent bundle, and then I substitute EI in this place, and I get a section of S again.
Is this Clifford multiplication or Clifford action?
Well, neither. So this is what we have here, and this is just a section, and then I Clifford multiply the section by the cotangent field EI.
Using that action?
Using the Clifford action, yes. Well, the formula is not very illuminating, and there might be a better way to define this operator, which I'm not aware of. So the Clifford, the operator is self-adjoint, so it's there is no point in calculating the index. We already know the index is 0. But if we manage to split S as a sum of quote unquote even and odd parts, then we get something interesting. And we saw a few examples. Yes, this operator is elliptic. Why? Because when the easiest way to say it would be to apply okay, let me apply d twice. Then I get multiplication by psi squared. But psi squared is simply minus the modulus of psi times 1. So in particular, psi squared is central, and it's moreover a multiple of the unit, and since the scalar product is a positive definite, this is never 0 unless psi itself is 0. We have seen a couple of examples. Example 1. Example 1, the exterior algebra of the cotangent bundle is isomorphic as a bundle to the Clifford algebra of the cotangent bundle. Well, the Clifford algebra acts on itself. So let's consider this action. It's well, straightforward to check that the action is parallel, which basically follows from the fact that we we have CL t upper star of x. This is simply P PSO cross SO Rn, where n is the dimension of x. And then we have, this doesn't make sense, CL n. Okay, SON. The standard Clifford algebra. Now, let's consider the multiplication on the standard Clifford algebra. Well, it's SON invariant. And this means when we globalize, we get a parallel multiplication. This is the trick we also saw on Saturday.
What is CLN?
This is the Clifford. This is the bundle of Clifford algebras obtained from the cotangent bundle. And by the way, the definition is here. We could use this as the definition of t upper star of x.
So CLN is just Clifford algebra responding to n-dimensional vector space with Euclidean.
Yes, with any positive definite, any fixed positive definite quadratic form. And there are analogues for non-degenerate but not necessarily positive definite forms, and these are interesting, but let's not overcomplicate things. Okay, the group SON acts on CLN by automorphisms. What does this mean? Well, this means the action of CLN preserves the multiplication. Well, okay. This means that the multiplication which we obtain if we take S to be CL t upper star of x is parallel. Because SON preserves because SON acts by automorphisms. Ну, можно явную формулу написать, и она займет полдоски. Но значит, на самом деле объяснение очень простое. Значит, действие СОН на алгебру Клиффорда — это действие автоморфизма алгебры.
Это объяснение чего?
Что?
Это объяснение чего?
Это объяснение того, что вот это умножение будет сохраняться при параллельном переносе. Но есть любители писать, то есть есть любители, которым проще написать формулу. Мне сложнее. Well, first of all, we take a connection on the principal bundle, and then we induce, starting from a connection on the principal bundle, we can induce a connection on every induced bundle. And sometimes the converse is true when the structure group acts faithfully on the fiber. The converse is true. Starting from a connection on the induced bundle, we get a connection on the principal bundle. Okay. Well, this was one example. And in this example, we have a decomposition of the CL into even and CL naught plus CL1. So basically, it's something we already considered when we talked about the RAM operator. Every element of every differential form is a sum of homogeneous components, and we have the even part, the odd part, and the same. The same is true for CL of t upper star of x, and we have this decomposition. And this time we get something interesting, namely we get the so in this example. The Dirac operator is the RAM plus the conjugate. Okay. Now we already saw that the operator from the even part to the odd part is interesting, and more precisely, the index of this operator is precisely the Euler characteristic. That's why it's interesting. And we also saw another example, the signature operator, and the signature operator is also a particular case of the Dirac operator, but the bundle is exactly the same. Although for the signature operator, I need here. I could talk about real vector bundles or complex vector bundles. The index is the same, and the splitting is the same. For the signature operator, I really need a complex. I really need to complexify before I introduce the operator. And but otherwise, the bundle is the same, but the splitting, the even-odd splitting, is different, and we get another operator which also has an interesting index, but this other operator will be, but the index will be different. It will no longer be the Euler characteristic; it will be the signature. well, we take S equal, again, lambda star of T upper star, but well, for the signature operator, let's assume that n is even. Then we have the complex volume form, which which we could view as as an element of CL times C, or we could view it as a parallel section of this bundle. So we get the same bundle, a different splitting. Okay, let's consider one other example, which we started talking about on Saturday, but didn't finish. Well, the Attea-Singer operator. Well, let's before we talk about this one, this operator, let's remember one of the interesting applications of this operator. In particular, today we'll probably see the main ingredients which are necessary to prove this application. An application is Rockland's theorem. What does Rockland's theorem say? Well, Rockland has many theorems, so which one? Well, the one I mean here is the following one. The signature of the signature of a spin for manifold is divisible by 16, where as often we assume that the manifold is compact, orientable, without boundary. Okay, so what is the spin for a manifold? Well, we'll see it in a minute. We'll see it in a minute, but probably we already mentioned it at some point on Saturday. A manifold is spin, if and only if, by definition, the tangent bundle has a spin structure. Okay, so well, before we discuss all this, let me mention another corollary, which is a corollary of this one. The E8 manifold has no smooth structure. Now, what is the E8 manifold? Well, it's a manifold which is basically, let's just say it's a manifold which is smooth, compact, orientable. No, smooth. Well, let's not get carried away. A compact, orientable, without boundary. Such that the intersection form on the middle cohomology is the form E8. Well, this form has over R. This form, the signature of the form is 8, and this does not divide. No, 16 does not divide 8. So, the manifold has no smooth structure, which is well, which is a good example of an obstruction for a smooth structure to exist. Anyway, and it's possible to construct topological form manifolds which indeed have E8 as the intersection form. The construction is well. The construction is straightforward, modulo the existence of a Casson handle, and the Casson handle exists. There is no doubt about that. The tricky part is proving that the Casson handle is a disk. And, it's well, it's something that takes quite a bit of work if one wants to do it properly. Anyway, are there any questions? Real dimension 4, and may or may not have a complex structure. Okay, well, and by the way, there is one other thing which one needs to mention. If I have a smooth manifold with intersection form E8, then this manifold is automatically spin, and this follows from Wu's formula. What does Wu's let me just put it here. whose formula expresses the the tangent or cotangent, doesn't matter, Stiefel-Whitney classes of a smooth manifold in terms of the cohomology viewed as a module over the Clifford algebra. Over the Steenrod algebra. Basically, in the four-dimensional case, all we need to know the A2 structure is the multiplication. There aren't any. There is which Steenrod operations are there? There's SQ2, which is just squaring from H. I need simply connected because let's say that simply connected intersection form E8. Then I apply Wu's formula. So if I know the cup product, I know the A2 structure, and then one does a calculation, and one finds that W2 is 0, which basically means there is a spin structure. Okay, does this make any sense? Okay, there is let's just assume that there is a way to express for a smooth manifold to express the Stiefel-Whitney classes in terms of the cohomology, but with an extra structure of A2 with the extra structure of a module over the Steenrod algebra. Let's assume the Steenrod algebra is an algebra which is quite large and which acts on the mod 2 cohomology of every space. Moreover, a map of spaces induces a map of modules over the Steenrod algebra. And the same is true for cohomology mod P. There is also a Steenrod algebra mod P, which is very similar to the one mod 2, and let's not get into this is an interesting topic, but let's not get into detail, or we'll never get out.
It's a general formula or for?
No, this one is only for mod 2, for the cohomology mod 2.
For any manifold or some special?
No, here we need to assume that X is compact, and I think this is yes. I think we need compactness, but this is it. We don't even need compact and smooth, otherwise it's not very clear what the tangent bundle is. And we don't even need. Do we need? I think we don't need the manifold to be orientable, because mod 2 everything is orientable. Okay, are there any questions, remarks, criticism? Okay, so the point of this remark is if the intersection form is E8, then and the manifold is compact and smooth and four-dimensional, then we can prove one can prove that the let me just so E8 W2 Ex so if the intersection form is E8, the second Stiefel-Whitney class is 0, and this means there is a spin structure. Okay, now the first application, the first arrow is just an application of Wu's formula, but what about the second one? Did we talk about spin structures and W2? Do we know what a spin structure is? I sort of hope we do, but
Well, we define it, but I don't remember.
okay, we defined it. Okay, well, let's briefly. Well, let's begin with oriented vector bundles. Well, if we have an oriented vector bundle, this bundle is obtained from some principal SO bundle, and then I say that either the vector bundle or the principal bundle admit a spin structure if and only if there exists a principal spin bundle and and a spin R map from this principal bundle to this principal. Does this diagram make any sense? Now, first of all, let's look at the diagram now, and if it doesn't make sense, let's make sure it does before we go any further. Пусть у нас есть ориентированное расслоение. Значит, построим векторное, построим по нему главное расслоение. Ну, поскольку все ориентировано, давайте предположим, что структурная группа уже там SOR. Ну, значит, дальше можно спросить, а вот существует ли такое главное спин-расслоение, спин-R, которое, значит, отображается в главное SOR-расслоение вот таким вот образом. Well, so what this means is the map. The map is a map of this map needs to be equivariant with respect to the action of spin R. Okay, now let's briefly see where there. What we need is there exists such a spin bundle and a map from the spin bundle to the SO bundle if and only if the second Stiefel-Whitney class of E is 0. Well, where does this thing come from? Let's see. Well, let me just briefly explain. I don't want to give full details, but let me briefly explain where this comes from. Okay, so the key remark. The map P spin to PSO is a double cover that is non-trivial over each fiber of PSO to X. Well, in one direction, this is clear. Basically, if we have a spin principal bundle, then and the map of principal bundles, which commutes with the action of spin, then over each X we have a double cover. But then some work is needed to prove that the converse is also true. If we have a topological double cover with this property, then this double cover is in fact can be made into a principal spin bundle. Does this make any sense, Volodya?
Well, actually, I don't understand what you're saying before that. I mean, you take a smooth manifold X. So you want to prove that some manifold has a spin structure, right?
I want to prove that the manifold has that a manifold has a spin structure if and only if the second Stiefel-Whitney class of the tangent bundle is 0.
Yes, but what was said before, I mean, on the middle of the desk, there, so there's some smooth manifold X. So I just don't understand what it has to do with the E8.
Well, here it says if I have a smooth full manifold such that the tangent bundle Tx has a spin structure, then the signature of the manifold is divisible by 16. And then as a corollary, suppose I have a manifold which is compact, orientable, simply connected, but the intersection form is E8. Then the signature is 8. It's not divisible by 16, so the manifold can't be smooth.
Yes, I understand.
Так, Володя, значит, значит, на каком шаге там возникло противоречие?
Может быть, у меня там было какое-то противоречие, но я просто... Но там еще говорит про формулу ВУ.
Да, значит, да, теперь мы, собственно, хотим, значит, хотим пояснить, почему, вот хорошо, у нас есть какая-то такая штука, у нее пересечение, там форма пересечения Е8. Ну и что? А почему из этого следует, что значит, на этой штуке есть спин-структура?
Да, но я уже смущаюсь, что мы говорим, что оно гладко.
Значит, да, значит, утверждение такое, пусть у нас есть многообразие, значит, которого форма пересечения Е8. Там компактное троллеля. Значит, предположим, что оно гладкое. Тогда по формуле ВУ, значит, применим формулу ВУ и, значит, и выведем, что W2 равно нулю. Тогда, значит, тогда у него есть спин-структура. И тогда мы к нему применим теорему Рохельна, получим противоречие. Okay, so basically I repeated this argument again. Suppose we have a manifold such that the intersection form is E8. The dimension is 4, and the manifold is oriented, simply connected, no boundary. Suppose the manifold is smooth. Then we can apply Wu's formula and get this. Then there is a spin structure, and then by Rockland's theorem, the signature is divisible by 16, but it isn't. So this means there is a contradiction, namely the manifold can't be smooth. Okay. Okay. Well, let's see. Let's see if we have time. Well, so we want let's try to answer this purely topological question. Well, I have PSO over X, a principal SO bundle. I want to know when there exists a double cover, which is non-trivial over each fiber. Well. What are double covers? Let's try to remember. We What is a double cover? Well, for double covers, we have a simple description. A double cover is the same as an element of the second cohomology group, mod 2. Does everyone agree with this, or not, or well, again, does everyone understand what a double cover is? Okay. Now, what are double covers? Double covers are maps from by 1 of X to the group to the automorphism group of a 2-element set. Well, there are just 2 automorphisms: the identity and the transposition. Well, normally, we should be talking about maps of groups from pi 1 to z by 2 up to conjugation. But, well, first of all, we can forget about conjugation. Z by 2 is abelian, so there is no conjugation. And second of all, in this formula, we can replace pi 1 by h1. Why? Because again, z by 2 is abelian, and then we basically arrive here. Okay. Let's have a break. It's a good time to have a break. Okay, and then we'll basically finish talking about spin bundles and so on. Значит, P1 Абелев, поэтому здесь я могу написать, извините, значит, Z по 2Z Абелев. Поэтому здесь я могу написать за те же деньги хом. Значит, хом из H1 Z по 2Z, но это то же самое, что H1 сверху. Но это уже формула универсальных коэффициентов. Okay, so let's have a break, and then we'll continue. cylinder. Okay, so let's continue. We're trying to understand when does a vector bundle, an oriented vector bundle, admit a spin structure, and and also if it does, then how many? We have this this remark which basically reduces the question to whether or not there is a double cover of PSO which is non-trivial over each fiber over small x inside capital X. And then we basically take the Leray spectral sequence. Let's assume for simplicity that P naught of X is trivial, then we have this this diagram which represents the second page. Well, let's see. So, well, first of all, the bundle is homologically trivial because why? Well, because the monodromy will be multiplication by will be multiplication by elements of SO, and these act trivially on the cohomology of SO because SO is connected, as opposed to O. O is not connected, but SO is connected. Okay, so so the E2 page is simply the cohomology of the base with coefficients in the constant cohomology of the fiber. And we have only one element of H2 of SOR, no, H1 of SOR, which is not trivial. And by general nonsense, if the second differential kills this non-trivial element, then this this class is this class. Then there is a global class which restricts to this class, and conversely too. Now, my claim is that this question mark is precisely the second Stiefel-Whitney class. And to see this, we first know that this element is natural, meaning it's functorial with respect to maps of principal bundles. And in the universal example, we have the universal example is x equal BSO and BSO and the principal bundle is ESO, in which case we have in which case we have this, and H2 is just Z by 2 generated by the second Stiefel-Whitney class. And in this case, we know that the differential is not zero. Why? Well, because not all bundles have a spin structure. And so in the universal example, the differential takes the only non-trivial element of this group to the only non-trivial element of this group. And by the way, another reason is in the universal example, this ESO is contractible. So, so this group must vanish, and this group must vanish, and there is no other way for them both to vanish, or in fact for either of them to vanish. Okay. So we've explained why there exists a spin structure if and only if if and only if there is if and only if we have W2 equals 0. Now, how many spin structures? Well, let me just briefly state the answer. If there exists at least one, then all the rest are in bijection with H1 mod mod 2, H1 of X mod 2. Why? Well, because if there is a global class which restricts to this class, then the other classes which restrict to the same class here must come from here. And what do we have here? Here we have the first cohomology group, mod 2. Okay, so we have explained this phenomenon. There exists a spin structure if and only if the second Stiefel-Whitney class is 0. Well, for every oriented vector bundle.
Why? Because we are working with
Because well, again, if we have an oriented vector bundle, we have the corresponding principal bundle and the Leray spectral sequence. It looks as shown here. And if pi naught of X is 0, which is well, which we can always assume, then the group here will be just Z by 2. Okay. Now the generator of this Z by 2 is globally defined if and only if the second differential is 0. What is the second differential? Well, the second differential, even if we don't know, it's functorial. Let's calculate it in the universal example. In the universal example, there is only one 0 element here, and only one non-zero element here, which is the second Stiefel-Whitney class of. By the way, I think I need to put a tilde here. It's oriented.
So with the same thing, and we can say a similar thing in this general example that for large n, if bundle is vertical, it is the Euler class. Right?
For large n, how large?
Not for the second, for example, not for the second cohomology. For n, the top cohomology would be the Euler class. With the same
I don't understand the question.
I mean, if we do the same method here, just in the universal example, can we say that the image of the nth differential would be Euler class?
The nth differential of what?
Of the 0n page to, no, sorry, to, I mean, instead of saying that the second cohomology of base is the utility class for the, I mean, top cohomology, you can say it's going to be the Euler class.
The Euler class of what?
The base. I mean, for tangent bundle. Or whatever vector bundle we have. If it is correct.
No, I don't understand the question.
I mean, so we apply the same thing here for the universal example. For if we have a orientable vector bundle, we apply the same thing, so we can say that the image of nth differential from for suitable indexes, the image of that thing will be the Euler class. I mean, just
The differential in which spectral sequence?
in spectral sequence for the nth stage from
The says spectral sequence of what? Of which vibration?
of a arbitrary weighted bundle. Is that true? Because the fact is
Okay, okay, I've understood the question. The answer is it's minus the Euler class.
minus or
And to be more precise, one needs to consider the spherical bundle, which corresponds to the vector bundle. On the spherical bundle, there is a canonical generator which lives somewhere here, and which corresponds to the Thom class, and it goes to minus the Euler class under the first non-trivial differential.
one more question. You know that, for example, I mean, is there something more general for higher classes? Because, for example, the first one is about orientability, the second one is for
Well, I'm afraid that's where it stops. I don't know of a similar interpretation for other characteristic classes. Okay. Let's see if we can get to the Atiyah-Singer operator. We're getting there, but we're not there. Not yet, anyway. Okay. So suppose we have a spin manifold, then we can take S to be what does it mean that X is a spin manifold? Well, this means in particular that Tx is BSO over SO Rn, and there exists a spin bundle, which covers the well, the corresponding principal bundle, and we have we can take we can take X to be a p-spin over spin p spin times m over spin, where m where m is a CLN module. Now, does this make any sense? And we it's straightforward to check that whatever I might take, it has a metric such that all elements of unit length in Rn act orthogonally. So and let me also mention this. And the metric is the metric is invariant with respect to spin, which we view as a subgroup of invertible elements of the Clifford algebra. Then we get a parallel metric on this bundle. Parallel with respect to to some spin connection on the spin vector bundle. Sorry, on the spin principal bundle. Okay, now what? Now, now we need to check that Clifford multiplication is also parallel. Well, Let's have a look. We have, well, we have well, we have the group spin, which acts on M and on Cl, but it acts on M by conjugations. Sorry, on Cl, on Cln by. And well, just by looking at this formula, what did I get? Well, well, suppose I have a G inside spin, then G and A inside Cl, N, and V inside M, and G, A, G to the -1. It has a GM. Well, G, okay. Now I use the fact that this is this is a module multiplication. So so if I take this element and act on it by this element, oh sorry, G AM, and so if I take this element of M and act on it using this element, I get this result, which is another way of saying that the multiplication has been invariant. So we get the Clifford action and it's again parallel, so we have the Dirac operator. Now we want to well, we want to calculate the index using well, first we assume from now on that n is even. By the way, the case of n odd is not particularly interesting, and the index of every operator on a non-dimensional manifold is actually 0, which is which is incidentally one of the problems I gave both of you as for the exam. Anyway, so let's restrict ourselves to this case. Well. Well, in this case, there is a unique irreducible CLN module, and well, sorry, CLNC, meaning CLN tensor C module. Well, if we have spin inside CLN, or more precisely CLN star, then it's also inside CLN cross C star. And in particular, it still makes sense to consider S of M, which this time round will be a complex vector bundle, not just a real vector bundle, a complex vector bundle, but why not? Okay, now the rest, well, the rest is actually quite similar to what happens when we calculate the index of the signature operator. Similar, but not identical. Well, let's see. In the index formula, we have two ingredients. One never changes. It's the total class of the complexified, well, either normal bundle or the tangent bundle. But the second ingredient is always a bit different from the previous case, and oh, and by the way, before we talk about ingredients, I need a splitting for this bundle. And I take the plus and minus splitting obtained using the complex volume form. Okay, does everyone remember what this is? Well, it's omega C, not W, and it's I to 1/2 n E1, etc. En. It's it's an element of the Clifford algebra. CLN tensor C, and we need C because we have an I to some power here, and then this element of the Clifford algebra induces a parallel section of the Clifford bundle, and then we using this we see that S plus and S minus the plus 1 and minus 1 eigen subbundles are actually subbundles and not just random collections of vector spaces. And the operator, the Dirac operator, interchanges plus and minus, and we want to calculate we want to calculate the index of the part of the operator which goes from plus to minus. Okay. Okay, so we take M. Well, as usual, we consider. There are two ingredients. One is the tangent bundle, and the other one the tangent bundle of X, which is the same whichever operator we take. And there is the second ingredient in the index formula, which actually depends on depends a little bit on the operator. Well, let's calculate this one. So we have BSON. And as we did, as we used this trick a few times ago, a few times before, we split. We take the universal oriented bundle over BSON, and then take the oriented splitting. Let's call this Q. These are rank 2 oriented subbundles. Okay, now okay. Well, let's take the universal bundle, pull it back to B spin. Well, my claim is my claim is the my claim is the result will have a spin structure. And similarly, if I take these bundles, pull them back to y prime, I get some bundles, and these have my claim is again these bundles have a spin structure. So let's at least write down this claim. Okay, so I have some bundle here. I put it, I pull it back, and I have some collection of bundles here. I pull them back. And my claim is that all those bundles have spin structures. Moreover, all those bundles have unique spin structures. Okay, let's have a look. First of all, let's see why the spin structures are unique. Well, this is the easy part. Well, first of all, we have the pi1 of B spin is the same as pi naught of spin, and this is 0. So pi1 is 0. So the space B spin is simply connected. Well, what does this mean? Well, this means that the group H1 with the mod 2 is 0. So there is a unique spin structure. Well, let's see. What about this one? What about y prime? Well, the space y prime is obtained from B spin and well, by the way, nobody asked what y prime is. There are one way to look at the space would be to say that it's the splitting space for the pullback of gamma tilde. So we use the usual construction for the splitting space, and we now the the space y prime is obtained from is an iterated vibration of B spin, and all fibers are oriented Grassmannians. G2 of V, where V is at stage 1 it has dimension n, then n minus 2, then n minus 4, and so on. Okay, now we don't know everything about those spaces, but we know something. And in particular, we know a cell decomposition for those spaces. What is it? Well, it's the Schubert cell decomposition. In particular, there aren't any in the oriented case. In the non-oriented case, there is yes. In the non-oriented case, there is no. Actually, well. Okay, it depends on what exactly we call the Schubert cell decomposition. And But anyway, the okay, so well, we actually we don't want we don't need those spaces to be simply connected. We only need we need them to have trivial cohomology mod 2, and we know that the cohomology of this space mod 2 starts in degree 2. There is nothing in degree 1. Anyway, but I still claim that those spaces are simply connected, and well, let's leave it as an exercise.
You want to say G2 tilde is?
Well, G tilde is the oriented Grassmannian.
Isn't it trivially simple to make it because it's orientable? Oh, no, okay, the converse is true.
Okay, now so there is a unique spin structure. Well, if there is one, now the question is why is there at least one? Well, let's calculate the Stiefel-Whitney classes. Okay. Okay. Now, where shall we leave this as an exercise? Well, I'll give you a hint. The map Q or Q prime do not necessarily induce an injection in do not necessarily induce an injection in the cohomology mod 2, but well, if we take the the second cohomology mod 2, then the map is injective. Again, we use the fact. Q prime. Let's erase the statement about Q. well, there, no, I think for Q the same should be true. Well, again, we look at the spectral sequence and we what do we get? We get basically the well, using the same argument, there is nothing that can kill the H2, so the map of the H2s is injective. Okay, so well, W2 is functorial. So if I manage to prove that W2 of the pullback is trivial, then W2 of the bundle itself is trivial. Well, what about the pullback? Well, the pullback splits. And it splits as well. In the same way as this one. So basically, what I need is basically what I need is I need to prove that the Euler class of each of these. Sorry, and by the way, it's En. So what I need is I need the Euler class of each of the bundles EI to go to an element of y prime, which is divisible by 2. And well, it's well, it needs some work, but it can be done. What's this thing doing here? Okay. Anyway, I'm tired, so well, as a result, I'm a bit lazy, and so unless there is a strong suggestion to explain this part in more detail, let's say it's an exercise.
I have just one question. I don't quite understand what is meant by, so does it mean that y prime is obtained from this spin by some tau of vibrations? So is it some kind of limit?
Well, or co-limit. It doesn't matter. What I mean is, let's look at the first stage. The first stage is we take the the bundle of oriented two planes inside the pullback of gamma let's okay. Let's take gamma n, pull it back. Let's pull it back to B spin. The result is gamma prime. Okay. Now inside this gamma prime, I take the bundle of oriented two planes, and then this allows me to split off a two-dimensional rank 2 summoned when I pull back the vector bundle. Then I repeat the procedure. Okay. So well, those vector bundles, and my claim is they're all spin. Now we use the same trick as the one we used for the signature operator. Namely, let's say CL and C is CLN times C. Okay, now okay, so there is a way to identify CL n plus 2 with CL and C, CL n plus 2C with CL n C times CL2C. So that the module m n plus 2 will be identified with the tensor product of the corresponding modules. If we have a tensor product of two algebras and a module over the first one, another module over the second one, the tensor product of the algebras over the same base, we assume that they are over the same base ring, will act upon the tensor product of the modules. So far it's just general nonsense. Okay, now what do we do with this? Well, let's first of all, let's take m equal m2. And let's calculate the well, the okay, so this formula suggests that we first need to see what happens when we take a rank 2 spin bundle and then use the and then use this construction. Basically, we take the corresponding well, the corresponding principal spin bundle, and then take the product over spin. And let's see. Well, let's first consider the case when R is when n is 2. And so we have E okay, now for well, in this case, yes. So the bundle is well, has a complex structure, and it's well, more of a unique, meaning there is but the bundle is spin. So the W2 is 0. W2 of V is 0. So my claim is the Euler class is even. So there are So there exists a unique bundle which I denote 1/2 L, and it's unique with the property. It's the unique bundle such that the Euler class of this bundle is the first Chern class of this bundle is 1/2 the first Chern class of L. Okay, now well, now my claim is S of M by the way, what is S of M in this case? Let's see. By the way, does anyone remember what the second Clifford algebra is? The first one is C, and the second one is no, actually, the first one is C cross C, and the second one is and the zeroth one is C, just C. The second one is 2x2 matrices of the zeros of the zeroth one. Okay, so the algebra CL2 is just 2x2 matrices over C. Well, it's not very hard to guess what the unique irreducible module is. It's just C2. The matrices act on C2 just by matrix multiplication. Okay, now I want to split. Okay. Well, C2 is it's irreducible as a module over C2, but it's not irreducible as a module over spin. Spin 2 well, spin 2 is just the circle, and there is a decomposition of the C2 into the plus and minus part. Into the plus and minus eigensubspaces of the complex volume form. Okay. Well, let me just write the answer. It's straightforward to check that in this particular case, the algebra, the subbundle S plus will be the opposite of 1/2 L, and S minus will be 1/2 L. And by the way, what's was the CH of S plus minus S minus? Well, it's e to the minus x over 2 plus, oh no, sorry, minus e to the x over 2, where x is C1 of L. So we have calculated the, what is this? Oh dear. Well, it's a new phone, and I don't know how to block it from turning on. Anyway, doesn't matter. Just put it aside, and I'd be surprised that if it just comes up on its own this way. Anyway, we have this formula. Okay. But what I wanted, well, we don't. Let's. Well, at least let's write the answer. So for rank 2 bundles, we have this. Okay. So for now using this splitting and and the splitting for well, the splitting for the pullback to y prime, we have this formula. What who's who in this formula? Well, let's see. So. Well, we have those bundles Li prime, which are obtained, which are the summands of the splitting for gamma. gamma tilde pulled back to y prime. Okay. Am I right that everyone is lost? Okay. Okay, then what I will do is I'll explain this in I'll explain these steps in more detail in problem sheet 5, and at the moment only one half of problem sheet 5 is on characteristic classes is online. I will append this for those of you who are interested, it'll all be there. Okay, I think this is it. We started late today, but since the audience is lost and the lecture is tired, there is no point in going any further. Anyway, it will be unfortunately there wasn't time today to talk about the proof of the index theorem. Let's say by definition, let's assume that no one's really interested in the proof of the index theorem for various reasons. But if this assumption is false, if there are people who are interested, please let me know by email, and then maybe we'll arrange an extra meeting and talk about that. План такой, что мы хотим определить отображение индекса на несколько более широком классе операторов. Именно псевдодифференциальных. Потом основной шаг доказательства – это доказательство того, что отображение индекса таким образом определенное обладает некоторым свойством функториальности. В каком смысле это все нужно понимать, как раз там я планировал обсудить, но не успел. Okay, so again, this is this is not strictly necessary, but if there are people either in this room or outside the room who want to talk about this, let me know by email. Okay, are there any more questions? You certainly have until the end of the semester, and maybe if the Learning and Teaching Office allows it, maybe also until the end of the holidays. Okay, then this is it. Thanks for being there, and let's call it a day.